I've put out this roadmap because I believe this is the direction to go, right? I'm focusing on, I've not put in the values. That's kind of on purpose. It's just to let me know I think this is a series of steps that I'm going to use to reduce the circuit. Any questions about that? Now I'm only going to look one step at a time. The 4 and the 12, they're in series, correct? So I have to use the rules of series to get what their equivalent capacitance is, and it's going to be 3 farads. I don't really think I need to do the work on that, but I will if you want. 1 over 4 plus 1 over 12 ends up giving you 4 over 12, which is, when you invert it, 3. We good? All right. So we've reduced our circuit. This is now our new reduced circuit. If I could take the 4 and 12 away, I could replace it with one 3 farad capacitor. However, I have another system that I'm going to reduce now. This part. I have 2 3 farad capacitors that are in parallel. Parallel elements get added together. So this is just going to be 6 farads. Any question about that? All right. This is my new reduced element. I have 2 capacitors that are in series. I'm going to do 1 over 6 plus 1 over 3, which is going to give me 3 over 6, or 2 farads. This is my equivalent capacitance. It represents the capacitance for the entire circuit. Any question about that? 12 volts was applied to the equivalent capacitance. Q equals CV. This will tell me the charge that was pulled from the battery to charge up this system of capacitors. And that looks to be 24 coulombs of charge, just 2 times 12. Sorry to bore you. Okay, ready to go backwards? All right. When we take and move backwards, it's important to know that these things don't apply equally. You have to understand the manner in which you apply this information. 2 capacitors in series will split up the voltage. So we can't take the 12 volts and apply it directly, because only part of that voltage is going to be applied to the 6 farad, and part of that voltage will be applied to the 3 farad. And based on Kirchhoff's laws, I know that they will sum to be a total of 12. However, I know that in a series element, all the capacitors in series will be at the same charge. So when I step backwards to a set that's in series, I apply the charge to each element. And I know many of you think you will remember this. You will not. It would be nice to see you write it down, especially if you weren't here last week. This is a good place to start. So I'm going to take the 24 coulombs and say there's 24 coulombs charged onto this capacitor and 24 coulombs charged against this capacitor. Now, we stop here and figure out the voltage on each element. And just taking Q equals CV, solving for voltage, that's going to be charge divided by capacitance. So I have 24 coulombs divided by 6 farads is going to give me 4 volts. And 24 coulombs divided by 3 farads is going to give me 8 volts. These 2 capacitors split up the voltage. It still sums to 12 volts. It's a good way to check your work and make sure your arithmetic is okay, especially if the numbers aren't so nice and neat like these. I'll point out I'm giving you nice and neat numbers, right? We're just kind of learning the process. All right. We're going to step back again. I'm going to notice right away that the 3 farad capacitor at the bottom is the same 3 farad capacitor I have on both circuits. There's no work to be done there. It's got to be 24 coulombs and 8 volts. But the upper element, this capacitor, is actually 2 capacitors in parallel. Parallel elements will have the same voltage. They have to. The charge will redistribute itself until the voltage across both capacitors is the same. So I'm going to apply the 4 volts here and the 4 volts there. Now, there was a total of 24 coulombs of charge distributed on the top capacitor. 3 times 4 is 12 coulombs. 3 times 4 is 12 coulombs. I'll point out the total charge spread out on the 2 capacitors in parallel sums to equal 24 coulombs. It has to. It has to have this balance. Any questions? I'm good. All right, we're at the end. A lot of these aren't going to change. So this is 24 coulombs, 8 volts. This is 4 volts. Oops. 4 volts, 12 coulombs. And all right, this is the only thing I have to deal with. This 3 farad capacitor is actually 2 capacitors that are in series. So let's see. I'm going to a set that's in series. I'm going to take the charge and apply it to both. So 12 coulombs, 12 coulombs. Any question about that? All right, again, voltage equals charge divided by capacitance. So 12 divided by 4, 3 volts. And 12 divided by 12, 1 volt. Had to be a total of 4 volts. 3 plus 1 is 4. We have successfully solved this circuit and found the charge and voltage across each element in the circuit. This is what stepwise reduction looks like. Any questions about this? Some of you made mistakes. Again, this is a process. It's not particularly hard, but it's a process. And I'll point out, this process isn't on your equation sheet. But this is. But it won't tell you whether you're supposed to apply the charge or apply the voltage when you take steps back through your circuit. That's something you're going to have to memorize. And as luck would have it, Owen has a question.
If the battery is only providing 12 volts, then how do the capacitors have a total of 16?
Where do you see a total of 16 volts?
4 volts on the right capacitor in the parallel series, 4 volts on the 2 in the repetitious parallel series, and then 8 volts on the bottom.
Are you sure that's what you're seeing? You're adding up all the voltage to the whole circuit. But that's not how voltage works. Pick one loop, Owen. One loop.
Never mind. Yeah.
No, I have to mind. So Owen's question is so common and a common mistake. So you guys need to pay attention. There is a potential difference applied to this circuit. And if you want to really understand circuits, this is not me answering Owen's question. This was actually me waiting for somebody to ask this question because it's appropriate that all of you know the answer. So although I make fun sometimes, this is an important distinction. From here to here, there is a potential difference of 12 volts, right? It's applied by the battery. The elements don't distribute the 12 volts. They distribute charge and energy, but they don't distribute the 12 volts. There is a potential difference of 12 volts applied from here to here, meaning if this is 0 volts, then going from here to this direction is an increase in potential of 12 volts until we get here. Now, a lot of people will simply take and add all these numbers together, thinking they represent the total voltage of the circuit. That's not what voltage is about. Voltage is about a change in potential. I can't go from the yellow part of the circle to the green part of the circle and go through every capacitor, can I? So if I pick a path to go from yellow to green, say this path, by how much will the potential be raised for an electron going in this path? 12 volts, correct? And similarly, that same electron, if it went across this path, by how much will its voltage be raised? 12 volts. Now, what is something that you can sum for the entire circuit? And this is a little different. You can sum the charge, because those were real things. Those are point particles that got moved around. So when I add 12 coulombs plus 12 coulombs plus 24 coulombs plus 12 coulombs. That's got to be real. Except again, I have this arrangement, right? The only thing that truly sums in the circuit is energy. That's the only real thing that you can sum in the whole circuit. You can't sum the charge because of the way the charge distributes itself. I can't sum the voltage because, again, it's about voltage change. But the system stores energy. That sums. You can sum the total energy in the circuit. So I can do 1/2 CV squared for each one of these. Add all of that up, and that is the one thing I can say about the circuit. That is a sum of all the elements in the circuit. Yes, sir?
Is that why this configuration, or not this configuration, but the series ones, they both have the same voltage? Because if it were to go like in a circle, it would have the same like voltage change in there.
Mhm.
I don't know if
I'm not sure if I'm understanding your question or if it's a question, not a question, if what you're explaining is what I understand. So try again.
So if you go like, if you're in the yellow, and you go up, left, up, right, and you keep going, you go back, down. and
So
then
if my
you
loop
do,
looked like this.
No. Like,
No, no, no.
Can you, wait, you can do a loop in the parallel, right?
Yeah.
Yeah, so is that like why that's proven correct? Because,
Like that loop?
yeah, is that why both sides will have 12 or 4 volts? Or does that prove why?
I'm not sure if it proves why they have 4 volts or if it's using the fact that both sides have to have 4 volts to equal it out. You know, it's hard to know. I mean, the truth is Kirchhoff's rules and conservation of energy is why both sides have to have 4 volts. To answer your question truthfully without like trying to decide whether it's the rule or the law that we're applying here, if this side had a different voltage than the sum of this side, then charges would experience a force to be pushed from one side to the other until the voltages were equal. So at that level, we understand that there's still electric fields that respond to changes in potential, and that electric field is going to move charges until the potential equals out under those circumstances. But it is true that this has to be the negative and the positive side, this has to be the negative and the positive side, and this has to be positive and a negative side. If we do this loop, I increase potential on the left side, right? Because I'm going from negative to positive, and I decrease potential on the right side, and yeah, that sum goes to 0. And that's exactly why, because Kirchhoff's rules, which is conservation of energy, has to be followed here. But I want to be careful about the way I say this. Kirchhoff's first rule is an application of conservation of energy as it applies to electric potential. Total energy in the circuit is still going to be about how the charges were separated and the electric fields that were created inside those capacitors, which is why we can sum the energy for the circuit. Does that answer your question? All right. What do you think? Do you guys want another practice one just to see if you're getting this? Okay. I purposely drew this in a manner that might be more confusing. Don't let it get to you, but it is purposely designed to be more confusing. I'd start by coming up with a quick roadmap on how you're going to reduce this. I still tried to keep the numbers easy-ish. You'll want that change. It makes things much easier for you. First, before we actually work this through, something to understand, you could rewrite this another way. I could say, all right, I've got a 6 farad, just starting here and going that way. I then notice that there is a break in the line. 2 of them, right? that would cover all of this. That'd be this one. You could write it like this. This would be the same circuit. So when you make some of these choices about the way you organize it, keep that in mind. Some of your reductions make it look like things are in parallel that aren't. If you're not going to include the battery, that makes it even harder sometimes. So